Welcome back to Calculus 2. Today we're going to talk about the ratio test and the root test. First, let's discuss the ratio test. Consider a series having non-zero terms. So none of these a sub k's are equal to 0. They can be positive or they can be negative. There are three cases. If the limit as k goes to infinity of the ratio ak plus 1 divided by ak, the plus 1 is in the subscript. This is the k plus first term. This is the kth term. If this is some number less than 1, then the series converges. Second, if the limit of the ratio is greater than 1, then the series diverges. By trichotomy, there's a third option. If the limit is equal to 1, then the test is inconclusive. There are examples where the limit equals 1, where the series converges, and there are examples where the limit is equal to 1, where the series diverges. So the test gives no indication one way or the other in this case. Before proceeding to the proof, let me give you an example where the ratio test would definitely be a big advantage. Let's look at the sum as k goes from 1 to infinity of 1 divided by k factorial. One key indicator of where you're going to definitely want to use the ratio test is whenever you have a factorial. We'll take the limit as k goes to infinity. In this particular instance, a sub k is 1 over k factorial. We have to write 1 over k plus 1 factorial over 1 over k factorial. That's equal to the limit as k goes to infinity of k factorial over k plus 1 factorial. A ratio like this is something you need to learn how to simplify. The absolute values don't matter here. K factorial is k times k minus 1 times 3 times 2 times 1, whereas k plus 1 factorial is the product from k plus 1 down to 1. As you can see, everything here cancels except for the k plus 1 in the denominator. We have merely the limit as k goes to infinity of 1 over k plus 1, and that limit is 0, and that is less than 1. We deduce from the ratio test that the series converges. Now, we'll prove the ratio test. We're going to suppose that the limit as k goes to infinity of the absolute value, ak plus 1 divided by ak equals some number r that is strictly less than 1. Let epsilon greater than 0 be given such that epsilon is smaller than the gap between 1 and r. Then there must exist a natural number n such that if n is bigger than or equal to this natural number n, then the distance between this and r will be smaller than epsilon. The distance between ak plus 1 over ak in absolute value and r is smaller than epsilon. We can rewrite this absolute value inequality as just an inequality. Adding r to each of these recall, we chose epsilon so that 1 minus r was bigger than epsilon. Epsilon was smaller than this value, which means that 1 is greater than r plus epsilon. You can see that this is less than 1. It follows then that the absolute value of ak plus 1 is smaller than r plus epsilon times the absolute value of a sub k. We have here kind of a recursive statement. You can see then that the absolute value of a sub 1 will be smaller than r plus epsilon times the absolute value of a naught. Similarly, the absolute value of a sub 2 will be less than r plus epsilon times the absolute value of a sub 1. But wait a minute. The absolute value of a sub 1 is smaller than r plus epsilon times the absolute value of a naught. And so this will be less than r plus epsilon squared times the absolute value of a naught. Similarly, a sub k will be smaller than r plus epsilon to the power k times the absolute value of a naught. It follows then that the sum, as k goes from at least n to infinity of the absolute value of a k, adding up in the tail at least, that's going to be smaller than the sum, as k goes from n to infinity, of r plus epsilon to the power k absolute value of a naught. The absolute value of a naught can be factored out of this sum, and we're left with a geometric series. This geometric series has a common ratio of r plus epsilon, and we've seen that r plus epsilon is less than 1. It follows then that this series, this geometric series, converges. The common ratio is r plus epsilon, which is bigger than 0 but less than 1. And that explains why this converges. So we get something smaller than infinity here. That means that the original series, at least in the tail, the first finite number of terms don't matter, convergence is entirely determined by what happens in the tail. The tail of our series will converge absolutely. We deduce that the original series converges absolutely. And hence converges. Now you see why we had to do alternating series before the ratio test. We had to know that theorem, that if a series converges absolutely, then it converges. That's the end of the proof of part 1. You can see, though, that if the ratio r is bigger than 1, you can convert to a geometric series that has a common ratio strictly greater than 1 and hence diverges. The equals 1 case is a little more delicate in that it's possible to show by counterexample that the series may both either converge or, in other cases, diverge if the ratio tends to 1. The ratio test allows us to pit certain growth rates against each other, and that should refine your intuition about which series converge and which diverge. As an example, suppose we have the series, the sum as k goes from 0 to infinity of 2 to the k divided by k factorial. Here, we're pitting exponential growth, 2 to the k, versus factorial growth, k factorial. Which one wins? Which one grows faster, exponential growth or factorial growth? If exponential growth is faster, then the terms should go to infinity and this should diverge. If factorial growth is faster, the terms should go to 0. Will it converge? Let's apply the ratio test. The ratio test is definitely indicated because we have a factorial present. We'll declare the test that we're going to perform. We'll execute that test. We have to evaluate these at k plus 1. And then divide with this thing evaluated at k. That's the same thing as inverting and multiplying. The factorial cancels in this way. All but the k plus 1 term will cancel. In the numerator, we have k plus 1 factors of 2, and in the denominator, we have k factors of 2. We can cancel out k factors of 2. This leaves the limit as k goes to infinity of 2 divided by k plus 1. The limit is obviously 0. That's less than 1, and therefore the series converges. We have all three parts that are required of you. We have the name of the test, we have an implementation of the test, including the condition for convergence in this case, and we have the conclusion of the test. As another example, let's consider the sum as k goes from 1 to infinity of k times 2/3 to the power k. If not for this factor of k, we would have ourselves a geometric series with a common ratio of 2/3. That we expect to converge. However, we have this pesky little factor of k right here. Let's use the ratio test. We'll calculate the limit as k goes to infinity. We replace k by k plus 1 everywhere in sight, and then divide by this factor as well. You can see that we have k factors of 3/2 and k plus 1 factor of 2/3. We can cancel all but one factor of 2/3. we're left with 2/3 times the ratio k plus 1 over k. In the limit as k goes to infinity, the k plus 1 over k goes to 1, and so the limit is 2/3, and that is less than 1. Therefore, the series converges. It might be interesting to analyze this last example in a little more detail. When k is equal to 1, you get 2/3. When k is equal to 2, you get 2 times 2/3 squared. K is 3, 3 times 2/3 cubed, and so on. There's a unique way of decomposing this, an infinite sum of geometric series. We can look at this as 2/3 plus 2/3 squared plus 2/3 cubed, and so on, but we're missing another factor of 2/3 squared. And we'll add on a 2/3 cubed, and now we're missing a factor of 2/3 cubed, and so on. The first line is a geometric series with common ratio of 2/3 starting at 2/3. The second line is a geometric series with common ratio of 2/3 starting at 2/3 squared, and so on down the line. As you can see from our formula for the sum of a geometric series, the first series is 2/3 over 1 minus 2/3. The second sum is the first term, 2/3 squared, over 1 minus the common ratio, which is 2/3. And then 2/3 cubed over 1 minus 2/3, and so on forever. As you can see, all of the denominators are 1/3. That gives us a factor of 3 out front. What's left over is 2/3 plus 2/3 squared plus 2/3 cubed, and so on. Another geometric series. With the first term being 2/3, we have 2/3 over 1 minus the common ratio of 2/3. Again, the denominator is 1/3, which you invert. That gives you 9 times 2/3. And the sum is exactly 6. In other words, not only can we prove using the ratio test that the series converges, in this particular instance, we can also calculate what the sum converges to. As we saw in a previous example, factorial growth beats exponential growth. In our next example, we're going to look at factorial growth versus k to the k growth. If you think about it, k factorial is k times a smaller number, k minus 1, times a yet smaller number, k minus 2, and so on down to 1. Whereas k to the k is k times k times k, and it gives you k factors of just k. K to the k growth will be faster. Let's apply the ratio test. We'll take the limit as k goes to infinity, k plus 1 factorial over k plus 1 to the power k plus 1 divided by the terms in the series, that's k to the k divided by k factorial multiplied on the previous expression. As you can see, we do get some cancellation. K factorial cancels here. But there are k factors of k and k plus 1 factors of k plus 1. If we split off one of these factors, we'll have only k of those. We can combine these as follows. we're going to have the limit as k goes to infinity, k plus 1 over k plus 1 times k plus 1 to the power k times k to the k. This k plus 1 cancels, and we're left with the limit as k goes to infinity of k over k plus 1 to the power k. As you can see, as k goes to infinity, this goes to 1. We have a 1 to the infinity case, which is an indeterminate case. It's not a L'Hopital's rule case, but it may be converted into one. Through the standard trick, we'll have the limit as k goes to infinity of e to the natural log of k over k plus 1 to the power k. We get access to this exponent using the property of logs, bringing it out in front here. Now, as k goes to infinity, k over k plus 1 goes to 1, natural log of 1 is 0, and this factor of k goes to infinity, so we get infinity times 0. Still an indeterminate case, still not a L'Hopital's rule case. One more maneuver and we can turn it into one. We'll write this as the limit as k goes to infinity of e to the ln of k over k plus 1 over 1 over k. All of this in the exponent. We now have a 0 over 0 case, a L'Hopital's rule case. The limit may, of course, be put into the exponent because limits pass through continuous functions. So we can write this as e to the power of the limit as k goes to infinity. The derivative of log is 1 over. When you take the reciprocal of a fraction, it flips the fraction over. But we need to multiply by the derivative of the inside. To do that requires the chain rule. We'll have the bottom squared. The derivative of the top is 1 times the bottom, which is k plus 1, minus the top times the derivative of the bottom, which is 1. All of that is divided by the derivative of 1 over k, which is negative 1 over k squared. To simplify this expression, we can cancel one factor of k plus 1 here. We'll have k plus 1 minus k. The k's will cancel. We'll have e to the power of the limit as k goes to infinity. What's left over is this 1. We have a k times k plus 1, and then this negative k squared flips up and is multiplied onto the numerator. We can cancel one factor of k, but it won't matter. We'll get e to the negative 1. E to the negative 1 is 1 over e. E is about 2.718, which means we have 1 over about 2.718. Whatever that is, it's certainly less than 1. We deduce from that that the series converges, and that shows that n to the n growth is much greater than n factorial growth. As we have seen, factorial growth is faster than exponential growth, but n to the n growth is faster than factorial growth. Is there a fastest growth rate? The answer is no. All you have to do is take n to the n, and you can keep on going as long as you need to get a faster and faster growth rate. Let's do another example. Let's do the sum as k goes from 1 to infinity, negative 1 to the k, square root of k over k plus 1. What do you expect will happen? You expect that since this is an alternating series, you could use the alternating series test. The terms definitely go to 0, since the power on k in the denominator is 1, whereas the power on k in the numerator is 1/2. So the terms will go to 0, and they should go to 0 monotonically in the tail at least, which means that the alternating series test should conclude that this series converges. However, what is the conclusion of the ratio test on this series? We know that this will converge by the alternating series test. Does it converge by the ratio test? We'll take the limit as k goes to infinity, and you do absolute values, which means we don't really need these negative ones. We multiply by the reciprocal. That's going to be k plus 1 here. Again, I don't need these negative ones, but I'll write them anyway just for completeness. These go away just because of the absolute values. In the limit, as k goes to infinity, k plus 1 over k plus 2 goes to 1. The square root of k plus 1 over the square root of k also goes to 1. The whole thing goes to 1. The ratio test then gives no conclusion. The ratio test has failed us here. Yes, we're very sad. We have to apply something else. Fortunately, we already know what to apply, the alternating series test. We'll now look at the root test. The root test also looks at a limit. The limit as k goes to infinity of the kth root of the absolute value, the base of k. If the kth root of a sub k is less than 1, then the series involving a sub k converges. If the limit is greater than 1, then the series diverges. And you guessed it, by trichotomy there is a third case. Third, if the limit is equal to 1, no conclusion. Concerning convergence or divergence. The proof of the root test is similar to the proof for the ratio test, so I'll leave that as an exercise. Let me give you an example that illustrates the idea behind what's going on the root test. Let's consider the sum as k goes from, say, 1 to infinity of 2/3 to the power k. Now I know that you know that this is a geometric series. We have these exponents k, and that's a key indication that you may use the root test. So rather than use the geometric series test, where we already know that this converges because it has a common ratio of 2/3, and that's smaller than 1, we'll use the root test. The root test says, take a look at the limit as k goes to infinity of the kth root of the kth term, 2/3 to the k. The kth root exactly cancels the power k, and we get 2/3, which is equal to the common ratio, and that's less than 1, and therefore this converges. For another example of where you would like to use the root test that perhaps isn't as obvious as, say, a geometric series, let's look at the sum as k goes from 0 to infinity of k plus 1 over 2k plus 3 to the power of k. You can see that in the limit, the quantity inside of the power of k goes to 1/2. And so this will eventually behave like a geometric series with a common ratio of 1/2. But we definitely would like to use the root test here, because the root test cancels out these powers of k. We'll take the limit as k goes to infinity, the kth root of k plus 1 over 2k plus 3 to the power of k. Of course, the kth root and the power of k cancels, and we get a limit of 1/2, which is less than 1, and therefore the series converges. Okay, another example. Let's look at the sum as k goes from 1 to infinity of e to the power 2k divided by k to the power k. Converge or diverge? What is your opinion? If you said converge, you are right. K to the k growth is going to beat this exponential growth in the raised to infinity. The terms will be driven to 0 so quickly that the series will yield a finite sum. What is the correct test to use in this case? In this case, because both of the factors in numerator and denominator have powers of k, you might try the root test. We'll take the limit as k goes to infinity of the kth root of e to the 2k divided by k to the k. This simplifies as the limit as k goes to infinity. This kth root will cancel this k here, ending up with a e squared. Kth root canceling the power of k in the denominator, leaving a factor of k in the denominator. The limit is, of course, 0, which is smaller than 1, and therefore the series converges, as we predicted. In another example, let's suppose we're dealing with the sum as k goes from 1 to infinity of k plus 1 over 3k plus 2. Converge or diverge? In this case, it looks like the terms of the sum are tending towards the value of 1/3. The divergence test tells us that if the terms don't go to 0, then the series must diverge. We will apply the divergence test. We'll just take the limit of the terms. We'll get 1/3, which is not 0. We deduce that the series diverges. Consider the sum as k goes from 0 to infinity of pi over 6 to the power k. Yes, this has a power of k, which means you may use the root test, which works great for geometric series as well. And that is a geometric series, so let's just use the geometric series test. The common ratio is pi over 6, and that means the common ratio has a magnitude less than 1. That means this series converges. Consider the sum as k goes from 1 to infinity of k e to the minus k squared. Converge or diverge? The negative exponent will drive this to 0 very rapidly, meaning you kind of expect that this will converge. What is the right test? Looks like the ratio test would be kind of messy. The root test won't help because you'll have the kth root of k, which is nasty. It looks like the best test here would be the integral test. We'll integrate from 1 to infinity x e to the minus x squared dx and see if we get a finite or a convergent improper integral. Both converge or both diverge. How do you integrate this? It looks like you need to do a u substitution. U is minus x squared. It has its derivative more or less lying around. The only thing missing is the factor of -2. We'll divide the -2 off on both sides here. And we get -1/2 the integral. Now, if x is equal to 1, u is -1. As x goes to infinity, u goes to minus infinity. We'll have e to the u du. Continuing to evaluate the integral, we have this -1/2, the limit as L goes to minus infinity. The integral of e to the u is e to the u. We'll have this evaluated from -1 to L. We'll have -1/2, the limit as L goes to minus infinity, e to the L minus e to the -1. And the limit as L goes to minus infinity, e to the L will go to 0. We'll have a negative is positive 1/2 e to the -1. And that implies that the series also converges, because both converge or both diverge. Let's look at the sum as k goes from 0 to infinity, and let's have k factorial over 10 to the power k. Converge or diverge? If you said factorial growth is greater than exponential growth, and since the factorial growth is in the numerator, that this should diverge, you were right. What is the appropriate test? Since we have a factorial, we should use the ratio test. We'll take the limit as k goes to infinity of k plus 1 factorial over 10 to the power of k plus 1, and then we'll multiply by the reciprocal, 10 to the k over k factorial. Reducing this fraction, we end up with k plus 1 in the numerator and just k in the denominator. K plus 1 is going to infinity, so the whole thing goes to infinity. That's greater than 1, therefore the series diverges. Consider the sum as k goes from 1 to infinity of -1 to the k times 5 divided by 7k plus 3. Converge or diverge? It looks like, since the terms go to 0 and this is an alternating series, that this should converge by the alternating series test. The only question is, does it converge absolutely or does it converge conditionally? If we ignore the -1 to the k, this 5 doesn't matter because it can be factored out. The 7 doesn't really matter. The 3 doesn't matter because when k gets big, we can ignore the 3. It looks like this series grows like 1 over k. like the harmonic series, which means in absolute value, we expect the series to diverge. We expect this to converge, but to converge conditionally and not absolutely. Now, all we have to do is prove what we just said. We'll use the alternating series test. We have to prove that the terms tend to zero, and they tend to zero in a monotonic fashion. So we'll take the limit as k goes to infinity of 5 over 7k plus 3, and that gives us 0. That's check number 1. The terms go to 0, but do they go to 0 in a monotonic fashion? To determine that, we need to take the derivative. When we take the derivative, this 5 doesn't really matter. The derivative of what remains is negative 1 over 7k plus 3 squared, because the derivative of 1 over x is negative 1 over x squared. But you need to multiply by the derivative of the inside, which is 7. You can see now that the square makes the denominator positive. The numerator, however, is negative. Since we get a negative derivative, that means the terms monotonically decrease. We may now deduce from the alternating series test that the series converges. But we're not done. We still need to determine whether or not the series converges absolutely or conditionally. To do that, we look at the series of absolute values of these terms. What test do we apply here? If we ignore all of the unimportant factors and terms, this looks a lot like 1 over k. Let's use the limit comparison test to the harmonic series. This is the harmonic series, and it diverges. Implementing the limit comparison test, we'll take the limit as k goes to infinity of 5 over 7k plus 3 divided by 1 over k, which is times k over 1. The limit is 5/7. Because that is a positive real number, we deduce that both converge or both diverge. Since the harmonic series diverges, this diverges as well. That means the series converges conditionally. You might be glad to learn that we're done with all of our convergence and divergence tests. What we need to do is practice, and that's why we need a lab.